If you're following along with our series, this is video CA5, number 5, and this will cover chapter 1.3a. It's just going to be the first part of that section. The link to that textbook will be in the description below. If you just jumped in for some help with radicals, then that's cool too. Our objectives for this video is to evaluate some square roots, to simplify some square roots, and add and subtract square roots. And notice this is all about square roots. We'll talk about some higher roots in the next video. First, our terms. A radical. A radical has the little square root sign. Now, the number under the radical is a radicand. So when I say radicand, you'll know that's the number I'm talking about. Your index is the little number inside your sign right here. And plural of that is indices, but this is your index. And for right now, if you don't see a number there, if you don't see an index, then that's understood to be 2. If it is anything other than a 2, there will be a number there. So if you've got a sign with no number, you can understand it as 2. So what is a radical? A radical is actually an operation sign. It's a mathematical operation, just like addition, subtraction, multiplication, division. And just like those operations are opposites of each other, a radical is the opposite of squaring a number. You can square a number or you take the square root of it. So let's just look at the square root of 49. You all know that's 7. But is it 7 or is it negative 7? Because you can multiply, you can take 7 squared, that gives you 49. Negative 7 squared is also 49. So we came up with a way in math to tell, does someone mean positive or negative? The first thing you're going to hear is a principal square root. A principal square root, now we're not talking about higher roots, but the principal square root is the positive. And you always assume that the person wants the principal square root unless you're told differently. How can you be told differently? Well, the presence of this sign, the plus or minus sign, would mean that they want both roots, not just the principal square root. So, if your problem says square root of 81, then you can just put 9 for an answer. But if your problem has plus or minus square root of 81, then you're going to put the plus or minus in your answer. If you'll think back to when you were using the quadratic formula and you had that plus or minus in there, that meant both roots. But for right now, we're going to be looking at principal roots. When we say evaluate or simplify a square root, what that means is we don't want the radicand to have any factors, numbers that will go into it, that are perfect squares. And I made a list of all the perfect squares from 2 to 15. Anytime I'm working with square roots, I always jot down a list of this over there somewhere, just so it makes it easier for me to see which numbers I'm focused on. So if my radical is in simplest form, that means that none of these numbers, and however far down you go, none of these numbers will go into this. So let's just look at some examples. Let's take square root of 100. Well, this is a perfect square. It's in my list. So what is the number when you multiply it times itself, you get 100. Okay? So knowing your perfect squares is going to be essential here. Okay, this is example 1b, square root of the square root of 16. Now a radical sign can also function as a grouping symbol, so you do what's under it first if possible. So I'm going to go to the innermost part. What's the square root of 16? Well, that's 4. So now what I have is the square root of 4. Now what's the square root of 4? 2. See how easy this is going to be? Example 1c, square root of 25 plus 144. What you want to do here, since this is a grouping symbol, we're going to do this first. 25 plus 144 is 169. 169 is a perfect square and its square root is 13. Example 1d, I have square root of 49 minus square root of 81. So like I said, these are grouping symbols. If we're doing PEMDAS, we're going to do the groupings first. The square root of 49 is 7. The square root of 81 is 9. 7 minus 9 is negative 2. Now I want to call your attention to the difference between the two problems that we just worked. This was the earlier one. This is the one we just worked. This one you have one radical sign and your sum is combined under that radical sign. So you need to add first and then take the square root. Now on this one, your square roots have an operation in between them. You have minus 49 minus 81. So you need to simplify each square root before you subtract. And it makes a difference. Let's just look at this. If I take the square root of 4 plus 9, and I do what's under here first, I get the square root of 13, which is 3.60 something, all right? If I split this up first and put square root of 4 plus square root of 9, well, the square root of 4 is 2, the square root of 9 is 3, so that's 5. You get two totally different answers, and this is why you have the order of operations. It's not that one was originally right and one was originally wrong. It's just that we tried to get consistent so that everybody gets the same answer. So according to the rules, you do what's in the grouping symbol first. If your problem says the sum under the radical, you just can't split that up. You cannot split up a sum. And I also want to point this out at this time. Every number has a square root. If it's not a perfect square, your square root is not going to be a whole number. For example, if I take the square root of 4, that's 2. If I take the square root of 9, that's 3. All these numbers in between 4 and 9, they have a square root. Let's just pick one. Let's say the square root of 7. It has a square root. What's it going to be? It's going to be in between these two numbers. So that would be 2 point something. You could use a calculator. But I do want you to understand every number has a square root. It's just not always a whole number. Those whose square roots is a whole number, we call those perfect squares. That's the difference. And I want to warn you about one more common little mistake. When you take the square root of a number, when you've performed the operation, you don't need that sign anymore. I see a lot of times people will, and I know you're not just thinking, you put that square root again. No, once you do the operation, you don't need the sign. If you've got 2 times 3, you don't put 6 times. Once you take the square root, you don't need the sign. What this leads to is, like if you've got square root of 16, when you take the square root of it, I'll see people do this. The square root of 16 is not 2. It is not square root of 4. It is just 4. So this is not correct. The square root of 16 is 4. So anyway, once you take the square root, you don't get to use the sign again. So now let's talk about a product rule. You're going to use this when you're trying to simplify your square roots. And the product rule says if you have two numbers that are multiplied by each other under the radical, you can split those up. Now, I just told you if you have two numbers that are added or subtracted, you can't split them up. But if they are multiplied, you can. Now, where's this going to come in handy? Well, let's look at the next example. We want to simplify the square root of 300. Now, it's not in simplest form as long as it has a factor, something you can multiply to get this, that is a perfect square. So which one of these numbers will go into 300? 100 will. So I can rewrite 300 as 100 times 3. Now I can split this up according to the product rule and get the square root of 100 times the square root of 3, which would be 10 square root of 3. Oops. Just a 3, not 30. So that's going to be your lowest term answer. Now let's look at square root of 12. If I ask you to simplify this, well, you're going to ask yourself, is there a perfect square that will go into this? And your answer is 4. So you would rewrite this as 4 times 3, which you can split up. And a lot of this you can do in your head. You don't have to write out every single one of these steps. The square root of 4, 2 onto 3. A lot of times I'll be asked, well, can you do this as 6 times 2? Because 6 times 2 is 12. Yes, it is. But I'm not interested in factors that are not perfect squares. So when you look at your radicand, you need to be thinking, you need to be focused on these numbers. These are the only things I care about. I don't care that 6 goes into 12 because 6 is not a perfect square. Now let's back up just a second and remember our product rules for multiplication. What was x times x? That was x squared. All right, what was x squared times x squared? That was x to the 4th. What was x to the 3rd times x to the 3rd? That was x to the 6th. Remember, you're adding your exponents. When you multiply bases, you add the exponents. So when we're taking the square roots of things, we're undoing that. So the square root of x squared is x. And the square root of x to the 4th is x squared. And the square root of x to the 6th, what did I multiply times itself to get x to the 6th? Is x to the 3rd. What about the square root of x to the 8th? What's that going to be? Well, what two numbers do you add together that are the same that gives you 8? It's going to be x to the 4th. Now, what do you notice about all these answers? The exponent compared to the exponent in your radicand. It's half of that, isn't it? So you can always take your exponent that's under here and you can divide it by your index. That's a rule we're going to get into in a lot more detail, but I want you to see that now. So if you're dealing with a square root, there is no index here or it's a 2, and you want to take the square root of it, all you have to do is divide that exponent by 2. Okay? Now, that's all well and good when your exponent is even. But let's look at what happens if I want to take the square root of x to the 5th. Well, you could put 5 divided by 2, but that's not going to help much. So simplified, what we want to do, we're going to do this the same way we just did the product rule. If I can put this as a perfect square times something else, then I can simplify it some. Right now it's not in simplest form because it has a factor that's a perfect square. What you do is this. We need even exponents, right? You can decrease, so you pick the exponent just underneath this one that's even. That's x to the 4th. You're going to multiply it by whatever you need to make this exponent. What is x to the 4th times x? It's x to the 5th. So I didn't change the value. Now you can split this up into square root of x to the 4th times square root of x, and you get x to the 2nd times x. Okay. Let's look at another one. What if I take y to the 11th? Okay. What is a number? What is the number just less than 11, but it's still even? That's going to be 10. So I'm going to rewrite this as y to the 10th times y to the 1st, or y. Now, what's the square root of y to the 10th? Y to the 5th. And that other little y is left under there. Okay? So you're just converting this to a product. One of your products is a perfect square. This is the same thing we just did with whole numbers. It's just we were only interested in these. Well, we're still only interested in perfect squares. What are the perfect squares of just a variable? Well, it's going to be anything with an even exponent. So we can even add that over here. Everything that has an even exponent is a perfect square, and its square root is half of the exponent. Next, let's have a look at example 2b on page 48. We have square root of 162, a to the 5th, b to the 4th. Now, first let's do we're going to simplify all three of these factors. Here's 1, 2, 3. And, if you're very fluent, then you can do all this at once. But for the benefit of those who, are still trying to learn this, I'm just going to focus on the 162 first. I'm going to get that whole number simplified first. So let's start off with, I need to know if there is a perfect square factor that will go into 162. So you can just get a calculator and start going down the list. It's not something that just readily jumps out at you. So 162 divided by 4 is 40.5. Well, I don't want anything that gets a decimal. So let me move to the next one. 162 divided by 9. 9 times 18. So if you want to stop there, 9 times 18 is equal to 162. But now your thought process should kick in. I notice there's a perfect square factor of 18. What can you break 18 up into? 2 times 9. So you could rewrite this even as 9 times 2. And then 9 times 9 would be 81 times 2. So now you have 9 square root of 2. Okay. So that is just the number part. Now let's see what happens to this other over here. Using the product rule, I'm following the rules, I could split this up into 162 times the square root of a to the 5th, b to the 4th. So now let's simplify those things. Remember, everything that you can take the square root of is going to come out from under the radical, and you're going to multiply it eventually times all the other things that are outside. So what's the square root of a to the 5th? Well, that's where you have to back it up 1. So I'm going to rewrite that as a to the 4th times a. Now b to the 4th, that's an even exponent, so I'm good there. I'm going to leave it like it is. What is the square root of a to the 4th? A to the 2nd. I have the a left under here. Now what's the square root of b to the 4th? B to the 2nd. Now when I combine these two things, whatever is outside the radical gets multiplied together. So 9a squared b squared, and then whatever is under the radical gets left there, 2a. Now, there are quite a few different pathways you could use to get to this same answer. So if you do different steps at a different time, that's all right. You know, this is just the way I think through it. But if you're getting the right answer and following your rules, you are perfectly fine. There is way more than one way to work this problem, I promise you. Now let's talk about the quotient rule. It's the same as the product rule, it's just for fractions. And what it says is if you have a fraction under the radical sign, you can split that up and find the square root of the top number and the square root of the bottom number. You can also use it backwards. If you have two square roots over each other, you can combine them under the same radical and simplify. When to use these is going to depend on your problem. If I have, say, square root of 5 over 36, and I look at this and I think, well, it's all under the radical. I can't simplify 5 over 36. That doesn't reduce down. But I notice, 36 is a perfect square. So if I use my quotient rule and rewrite this as 5 square root of 5 over square root of 36, I'll have to leave square root of 5 like it is, but I can reduce this to 6. That would be simplest form. Now let's use that product rule backwards. Instead of having one big radical sign with a fraction under it, I have a fraction with a radical in the numerator and the denominator. None of this is perfect squares, so it can't be reduced down. It's going to be a mess. So let's put it all under one radical sign first. So I'm going to have 234 x to the 11th y over 26 x to the 7th y. And let's see what we can reduce down here. Well, I know I can reduce these, and just because I know how books do, I'm going to do 234 divided by 26. And see, these go into each other perfectly. So as far as reducing down, 234, 26 will go into 234 9 times. So that would be a 9, a whole number 9. Now, x to the 11th over x to the 7th. When you have a fraction, what do? Subtract your exponents and put your exponent put your new answer where the largest exponent was. So 11 minus 7 is x to the 4th. And then y over y is just 1. Square root of 1 is 1. So we're done there. Now look what we have. 9x to the 4th. What's the square root of 9? 3. And the square root of x to the 4? 2. One step at the time. If you just look at this problem and start trying to do it in your head, you're going to get overwhelmed. Write your steps down. Don't be afraid to use paper. Okay, let's wrap it up by looking at how to add and subtract radicals. When you are adding and subtracting, you treat a radical just like a variable. If I had 3a plus 2a, I'm going to get 5a. Your a stays the same. You just use it to match, and then you add the coefficients. It's going to be the same way with a square root. If I have 3 square root of 5 plus 2 square root of 5, first of all, these radicals have to match. They have to have the same index. They have to have the same radicand. Otherwise, you cannot combine them. But since these match, what do I actually have here? Well, I've got 3 square roots of 5, and I've got 2 square roots of 5. So when I count them up, I've got 5 square roots of 5. I don't have a square root of 25. I did not multiply these together. You were just adding the coefficients. This is example 6, page 60. The trick is you can't just say, oh, I can't add those because the radicals don't match. You have to be sure that the radicals are in simplest form first. So let's go back and use some of those techniques. Let's look at this 12. Is there a perfect square that will go into 12? 4 will. So I'm going to rewrite this as 4 times what? 3. Now remember, 12 is equal to 2 times 6, but 2 and 6 aren't perfect squares. That's why I'm not using them as factors. I want factors that are perfect squares. Now what is the square root of 4? 2. When you pull that 2 out, this was actually a factor. Broken down, this is what you have right here. So when you took the square root of 4, now it's a factor, so simplified, you're going to have 10 square root of 3. Okay. Now let's come over here to this. 2 is in lowest terms, so I get to skip all the way down here and just put 2 minus square root of 3. Alright, so what is 10 square root of 3 minus 2 square root of 3? 8 square root of 3. So get them, if you look at some numbers or if you get a problem where these things don't match, you know you're probably going to have to simplify them. They have to be simplified before you can just say, oh, you can't add those. Now if I had 2 square root of 5 plus 3 square root of 7, you cannot simplify that because there is no perfect square that will go into 5 or into 7. They cannot be simplified and they do not match. So this is simplest form right here. You can't combine anything. So let's wrap this up with example 7 on page 50. This is a subtraction problem. These don't match, but they're not in simplest form. So I have two mini problems here to start with. I've got to simplify each one of these things. Now a few minutes ago that was a whole problem. Now that's just a part of a problem. So that's how we're building on stuff. All right, let's look at this one first. Now what I actually have here is a string of factors. This is actually 20 times square root of 72 times square root of a cubed times square root of b to the 4th times square root of c. See how that goes? So don't let yourself get overwhelmed. Don't look at this and say, oh, I've got to find the square root of the whole thing. No, just find the square root of each thing at one time. Now whatever I pull out of this radical, I'm going to multiply it times 20. So I'm just going to put the 20 over there. Let's do this by breaking down each of these things into a perfect square times whatever else. Alright, 72 first. Is there a perfect square that goes into 72? 9 does. So I can write this as 9 times 8. Now if you remember back in that earlier problem, I got into difficulties because I left one of my factors with a perfect square factor and then I had to kind of back up. So let's not do that this time. What is a perfect square that goes into 8? 4. So I'm going to rewrite the 8 now as 4 times 2. Now could you go ahead and multiply 9 times 4 and get 36 and then take the square root of that? Yes, you can. If you look at it, what's the square root of 9? The square root of 9 is 3. What's the square root of 4? 2. What is 3 times 2? 6. What's the square root of 36? 6. So either way you want to do that works. Alright, and then I've got my 2. Alright, a to the third. Now what do we do when something has an exponent that's not even and we want to take the square root of it? Take that base and back that exponent down to the next even number. That's going to be a squared, and then multiply it times the base one more time. So you're just trying to rewrite these things, but you don't want to change their value. Alright, b squared. Do I need to b to the fourth. Do I need to rewrite that? No, because the exponent's even. So you can leave it like it is. And then I have that c down there on the end. Okay? So all I did on that step is I went through these numbers, or this term, and I rewrote every part of it into a perfect square, if possible, times something else. Alright, I've got my 20 still over here. What I'm going to do now, everything that's a perfect square, I'm going to pull it out. And it's going to be multiplied times 20. So what's the square root of 9? 3. What's the square root of 4? 2. Alright, I'm going to put a radical over here so I can leave some stuff under here. The 2 is not a perfect square, so it can't come out. It's got to stay under here. A squared. What's the square root of that? A. So it gets to come out. The plane A has to stay under there. B to the fourth. What's the square root of that? B squared. So it gets to come out. And I've used these. And then all that's left is that C. Alright? All I did on that step was pull out the square roots of any perfect squares. Now let's clean this mess up. I've got to multiply 20 times 3 times 2. Well, that's 6 times 20, which is going to be 120a b to the second. Now the radical part is going to stay right here. Okay? That's the first half of the problem. So let's come over here and let's do the same thing to this one. The 14 is going to stay outside. And I'm fixing to go in here and I'm going to rewrite all of these things as factors, perfect square factors. Is there a perfect square that goes into 8? 4 does. So I'm going to rewrite 8 as 4 times 2. Now a to the third, just like over here, I'm going to rewrite that as a to the second times a. B to the fourth, I'm going to leave it alone because that exponent is even and I can take the square root of it. C, there's nothing I can do to that. Now let's see what all we can pull out of here. That's a 14. The square root of 4 is 2. 2 is going to have to stay under the radical. The square root of a squared is a. The a will have to stay under the radical. The square root of b to the fourth is b squared. And c is going to have to stay under the radical. Okay? So when I simplify this to get all my multiplication done, 14 times 2 is 28. A b to the second, square root of 2ac. Now, look at the wonderful thing that just happened to your problem. All of this matches all of that. Not even just the radical part, but all of the variable part matches. So that means you can combine these terms. All you have to do now is 120 minus 28, which will leave you 92. So we have 92, and this is ab squared radical 2AC final answer. Now for practice, you should be ready to work any of the problems 1 through 27 on page 55 and 56. So go ahead and work through those. You should at least do all the odd ones. If you're having trouble, work the even one right next to it. All math textbooks are set up, I don't know if you've gotten this, to where number 5 and number 6, they're exactly alike, just different numbers. The answer to number 5 is usually in the back of the book. So you work the odd one and check your answer, and then you can work the even one, if you need some more practice. But they're coupled like that. So work all the odd ones. If you get them all right, you're good to go. If you don't get them all right, come see me. And I will see y'all back here in the next video, which will still be some more of 1.3. I think it's going to be rationalizing denominators, but I'll see y'all in CA6.